Okay, in this video tutorial we are going to discuss this problem. A cantilever beam AB, 2 meter long, carries a uniformly distributed load of 1.5 kilonewton per meter over a length of 1.6 meters from the free end. Draw the shear force diagram and the bending moment diagram for the beam. Okay, this is the problem we are going to discuss. As the first step, you should draw the free body diagram for the entire beam. Okay, let's draw a free body diagram for the entire beam. See the beam. So then this end is a fixed support. You all know the fixed support, how to mark the support reactions. The A end, RAY, RAX. Let's take the bending moment, MA, at the A end. So then there's a uniformly distributed load. The intensity of the distributed load is equal to 1.5 kilonewton per meter. Then we have to mark the dimensions. The total length is equal to 2 meters. And this distributed load is acting 1.6 meter length. Then here you can see this distributed load is acting 1.6 meters, and the intensity of the distributed load is equal to 1.5 kilonewton per meter. That means if you take the meter length, the total load is acting is equal to 1.5 kilonewton. So here 1.6 that is acting 1.6 length. So the resultant of this distributed load we can mark the 2.4 kilonewton. They acting at the middle. You can see all of these are parallel forces. The resultant of the parallel forces acting at the middle. This load is equal to 2.4 kilonewton, resultant of the distributed load. Then this length is equal to 0.8. This length is equal to 0.8. So this length is equal to 0.4. Okay, this is the free body diagram for the entire beam. As the first step, you should draw this free body diagram. Then you have to find all of these unknown reaction forces from the support. To find RAY, I am going to resolve the forces in vertical direction. RAY minus 2.4 is equal to 0. So then RAY is equal to 2.4 kilonewton force is acting. Then by resolving the forces in horizontal direction, RAX is equal to 0. There is no any horizontal forces. So by taking the moment around this A point, this is the A point. Let's take this point as C and this point as the B. By taking the moment around this A point, here MA force, here you can see a resultant force, moment produced by the resultant force. The length to this point is equal to the 0.4 plus 0.8, 1.2. The direction is clockwise, so 1.2 into 2.4 is equal to 0. So then MA is equal 2.88 kilonewton meter. This is the moment produced by the fixed support. Then next step, you have to divide the beam into a segments so that the loading is continuous. You can see if you take A to C region, the loading is continuous. There's no load acting, external load acting on the beam. Then if you take the C to B region, you can see the loading is continuous. That means the distributed load is continuous from C to B. So I'm going to divide this beam into two segments, A to C and C to B. So that means A to C the loading is continuous and C to B loading is continuous. So we are going to obtain the separate set of equations for shear force and bending moment considering beam A to C region and C to B region separately. Okay, let's see how to obtain this set of equations. First, I am going to consider the A to C region. Let's consider A to C region first. To obtain the A to C region, you have to introduce imaginary cut in between the A and C at the x distance from the left hand side in. So I am going to introduce the imaginary cut somewhere in here. The x distance from the A sub A end, here the distance is x. So then I am going to consider this left hand side beam part. Okay, let me draw the left hand side beam part. That means we have to draw the free body diagram for the left separated beam part. Here this is the separated beam part, this is the AN. Then these are the forces acting, the 2.4 kilonewton force and also the moment MA, the 2.88 kilonewton per meter. And also we have to mark the shear force and bending moment. This is how we are marking the shear force in positive way, and this is the bending moment we are marking positive way. Let's take the bending moment and the shear force, the magnitude of shear force SF and the bending moment. Then I am going to obtain this equation for shear force and the bending moment considering the equilibrium of this separated beam part. So I am going to resolve the forces in the vertical direction to obtain the equation for shear force. Here upward force the 2.4 minus shear force is equal to 0. So then the shear force is equal 2.4 kilonewton. This is how shear force is varied throughout the length of A to C. Okay, then let's obtain the equation for bending moment. To take the equation for bending moment, I am going to take the moment around this A point. By taking the moment around this A point, here 2.88 moment produced by the fixed support plus bending moment minus this length is equal to x, shear force into x is equal to 0. This length is equal to x. This length is equal to x. Here 2.88 plus bending moment minus shear force. Already we have calculated the value 2.4 kilonewton into x is equal to 0. So then the bending moment equation we can write the bending moment is equal to 2.4x minus 2.88. This is how the bending moment is vary throughout the length of A to C. So then we can obtain the bending moment at x is equal 0. At this A point, the bending moment is equal to minus 2.88. The bending moment at x is equal C point. Sorry, 0.4. That values, if you substitute the 0.4 in here, you will get minus 1.92 kilonewton meter. Okay, then we are going to consider the C to B region. To obtain the equation for C to B, then I have introduced the imaginary cut in between the C and B, the x distance from AN to this imaginary cut. So then you can consider the left hand side part or right hand side part. In this case, considering obtaining equation considering right hand side part is easy. So I'm going to draw the free body diagram for this right hand side part. Okay, this is the part. Okay, then the distributed load is acting on this separated beam part like this. This is the distributed load. Then the length of this portion is equal to, the total length is equal to 2 meters. Then up to this point is x, so that 2 minus x length. Then this is very important, the marking the shear force and bending moment. Here we are considering the right hand side face. The right hand side face, you have to mark the shear force like this, shear force and the bending moment, you have to mark like this. If you are considering the left hand side, you should mark the shear force, you should mark in downward direction and the bending moment in anti-clockwise direction. Okay, this is the free body diagram for the separated beam part. So then I am going to obtain the equations, consider the equilibrium of this separated beam part. Okay, first of all, let's obtain the equation for shear force. So I am going to resolve the forces in the vertical direction. Shear force, then the distributed load minus the intensity 1.5, the length it is acting is at 2 minus x equal to 0. Here we have to mark the intensity 1.5 kilonewton per meter. Then the shear force equation is equal to minus 1.5x plus 3. This is the shear force equation. This is the shear force equation. Then the shear force at x is equal to 0. But when shear force x is equal 0.4, this region is starting at 0.4. Here C to be a region we are going to consider. So that value is equal, if you substitute this value in this equation, we will get the 2.4 kilonewton. Then the shear force x is equal at this end 2, that value is equal to 0. Okay, that value is equal to 0. So then I am going to obtain the equation for this bending moment. Let's take this point as O. So then I am going to take the moment around this O point. The clockwise moment I am going to consider. Then the bending moment plus, here the resultant of this distributed load acting in the middle, because all of these are parallel forces, the resultant is equal to 1.5 into 2 minus x. This is the resultant of this distributed load acting at the middle. Acting at the middle mean the distance from one end is equal to 2x minus divided by 2. Okay, by taking the moment, the 2x 2 minus x divided by 2, the length from O point, the magnitude 2 minus x into 1.5, then this is all the moment, that is equal to 0. Then the bending moment plus 1.5 divided by 0.75, 0.75 is square of this 2 minus x, 4 plus x square minus 4x equal to 0. Then by making the bending moment into subject, we are getting the bending moment is equal minus 75 x square plus 3x minus 3. This is the bending moment equation. This is how bending moment is vary kilonewton meter. Then we have to obtain the bending moment at x is equal 0.4 at this end, the bending moment. Then by substituting the 0.4 in this equation, you can use your calculators to find that value. That value is equal minus 1.92. Then the bending moment at x is equal 2. If you substitute the x is equal 2 in this equation, the answer is equal to 0. Here you can see this is the parabola having the maximum. It's a negative coefficient in for the x square. So parabola having the maximum. So when you're going to draw the shear bending moment diagram, you should know the symmetric axis and the maximum value. So then in this equation, the symmetric axis, you can get axis is given by this equation minus b at 2a. So then in this case minus b 3 divided by 2a minus 0.75. So then answer is equal to 2. That means x is equal to this parabola having the symmetric axis. X is equal to, at the x is equal to this parabola having the symmetric axis, and x is equal to its value become maximum. We have already calculated the maximum value, that is equal to 0. Now we have all the set of equations for A to C region and C to B region. Then we can then we are going to draw the shear force and bending moment diagram. Here you can see all the equations we obtain. I have listed in here. The shear force in A to C region, this is how the shear force is vary, and the bending moment, this is how the bending moment is vary. In the C to B region, this is how the shear force is vary, and the bending moment, this is how the bending moment is vary. So then now we are ready to draw the shear force and bending moment diagram. If you take the A to C region, how the shear force is vary, shear force is equal 2.4 kilonewton throughout the length of the A to C. That means that is constant. So I will mark that value, the 2.4. Let's not vary with the it's a constant throughout this length. It's a constant. Then after in a C to B region, how the shear force is vary. Here you can see it's a linearly varying. It's a negative gradient equation, linear equation, negative gradient linear equation. So then if you know the 2 points, we can draw the line. So a shear force at x is equal to 0.4. That means at this point, this value is equal to 2.4. The same at here. And x is equal 2 at this end, the shear force is equal to 0. So then this is how the shear force is vary. This is how shear force is vary in C to B region. And now we are ready to draw the bending moment diagram. If you take the A to C region, how the bending moment is vary, the equation is a linearly varying with the positive gradient. Positive gradient is equal to 2.4. If you know the 2 points, we can draw the straight line. Bending moment at x is equal to 0. That value is equal minus 2.88. So let me mark the point. Somewhere in here. Then x is equal 0.4. That is also negative. Minus 1.9. Somewhere in here. here 2.88. Yeah. Okay, let me draw the line. Okay, this is how bending moment is varying through the length of A to C. Then if we take the C to B region, this is how bending moment is varying. Here you can see it is a parabola. Symmetric axis. Where's the symmetric axis? X is equal to is the symmetric axis. So x is equal to mean this axis having the maximum at x is equal to, that means at this point the parabola should be maximum. So then this curve like this, parabola. So I will draw the curve like this. Okay, then this is how in C to B region the shear bending moment is varying. Okay, this is how we are drawing the shear force and bending moment diagram for this problem. Okay, if you learn something from this video, please like the video. Okay, see you next time. Thank you.